Bismillahirrahmanirrahim. This is the second video from chapter number 4 of DLD by Moris Mano. And here we'll be discussing design procedures. This is primarily a theoretical type of a concept building process. So you have to pay a little more attention. Let's see. Just recall that we know that like 1/4 is a decimal number, base 10. Then we come across a term called BCD, that is binary coded decimal. And if you write it like this, that the decimal number coded in binary, that means like this 4 is written as in binary 4 and 1 is written as 001 in binary. So this is the decimal number has been coded in binary, and that it is called BCD. But then there is another number set that is called binary number. Now this is 14. We know this value 2 raised to the power 0, then 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3. That is 8, 4, 2, 1. And if you add 8, 4, 12 and 2, 14, so this is equal to 14. So this is in binary form, but this is in BCD form. So you have to keep this in mind. But what is important in this explanation is Excess-3 BCD code. Now, what is Excess-3 BCD code? Each decimal digit, like if it is 0, is incremented by 3. Added 3, so it becomes 3 decimal system or 3 in decimal before being converted to binary. After this has been written, or 3 added, and then we convert into binary. So that is what is called is Excess-3 BCD. And it is very commonly used for error detection. So when you go further in this subject, then you will come across the error detection technique. For time being, just remember what is Excess-3. Now the design procedure has a few steps, that is determine the required number of input and outputs and assign a symbol to each. So like we'll be giving A, B, C, D to the input, and output we can call F1, F2, etc. The next step is derive the truth table, then obtain the Boolean functions for each output, and then draw the logic diagram. Okay, now we'll discuss about the need of code conversion. Now, let's say we have two digital systems. One understands only the BCD. So input is BCD, output is BCD. And there is another digital system which only understands Excess-3 code. So Excess-3 in, Excess-3 out. Now, if you want to connect this system with the Excess-3 system, what we need is a code converter. In between, it's just like a translator. If you have, one language and you are talking to a person of another language, then you got to have a translator in between. So code conversion will convert the BCD to Excess-3. And so in truth table form, we can say this is our BCD values 0, 0, 0, 0, 0, 1, etc. up to 9. And if you add 3, so like this decimal value is 0, adding 3, we get 3. So this is 3, 0, 0, 1, 0. Similarly, with decimal 1, if you add 3, it will be 4, and 4 in binary, we write like this. So this is how we get the Excess-3 codes. And now how to design a system which will do this job, code conversion function. Okay, to do that, this was our input and this is our desired output. For this, what we'll do, we'll take one of the outputs at a time. So let's say the W output, we have just copied it here. And we'll simplify this with the help of a K-map. I hope you have learned K-map. If not, then you must watch my videos on K-map, chapter number 3. Okay, now in the K-map, these are the values written, or you can write yourself. For 000, it is called M0. For 0001, it is M1, etc. Now, for ease, I'm just writing M0, M1, so we can easily plot it here. Now, just ignore the zeros and see where is 1. So M5 is 1. And so in this table, you can see M5 is 1. Then M6, 7, 8, 9. 5, 1, 6, 1, 7, 1. 8 is also 1. 9 is also 1. So these are the 5 values. We also know that since we don't have the numbers 10 to 15, therefore they are marked as a don't care conditions. So you can use them as a 1 or as a 0 to simplify. So this is our K-map, and now you can simplify. We should be getting this answer. I'll just show you one step, although it's kind of a repetition. But let's see this one. So 1, 1, and we take all these as 1, 1 excess. Therefore, this whole we can combine. And from here, you can see what is common. The only thing common is A, and nothing common from the top. Therefore, this will write A. Next, these 3 ones are left. We can combine 2 of them. So these 2 combining makes 4. And so they will be what? Look to the left, it is B on both sides. And from here, it is D on both sides. So BD. And similarly, now this is left. So we can group again these 2. Okay, so these 2 and excess make another group. And here also you can see it is B and then it is C. So BC. So this is how you get the first output W in terms of a Boolean functions or Boolean values. And same way, we can now take the other one, X, right, M0 to M9, plug in here, and you can solve. Now you can see we can group this and this to make 4. And this will be what? Let's see what is common. 1 here, no common here. 0, 0 is common, so it is B dash. B dash, and what is common from here is D on both. So B dash D we get, and similarly combining these pairs we get B dash C, and combining these 2 we get B C dash D. So this is X. Similarly, Y, you can combine this and this. One group, other group, and these are the 2 values. And then finally, Z. Now these are to the end, therefore we can just combine them to form 8. Just like this. Combining form 8, and therefore what is common? Nothing from this side. 0, this one, and this one 0, therefore D dash. So output Z is D dash. Okay, so we got these 4 values. Now the easiest way is to draw or form the sum of product form using 2-level logic diagrams. So you can just draw yourself. Like here, W is combination of 3 sets. So I'm using a 3 OR gate, 3 input OR gate. And you can just follow this. I have just done each set like this. So these are the 4 outputs, W, X, Y, and Z. Now, you can see there are two logic levels. One is the first level and the other is second level. And in these two levels, not counting the inverters, so we are ignoring the inverters, the implementation in sum of product form, these are called sum of product form without any simplification, requires 7 AND gates. So you can count from here 1, 2, 3, 4, 5, 6, 7 AND gates and 3 OR gates. Okay, now let's see if we can further simplify this. So this circuit in the book has been shown, and this is simplifying or minimizing the number of gates. And now this is 3 levels. You can see this is the first level, second level, and third level. And here we have 4 AND and 4 OR logic gates. So 8 logic gates, and here we have 10 logic gates. So don't laugh that there is hardly any difference between the two. But when you talk or think of the mass production, then even one gate matters. But anyway, these are pros and cons. It can be discussed. Now, how did he achieve this diagram in the book? So let's see. What he has done is this circuit tried to group further so that we can use this term C, D, or C or D. And C or D has now been used at 3 places, here, here, and here. So one gate actually used at 3 places, and that is minimizing. Now, how do you use this? So from the first one, we just take common. We take common B, so it is C plus D. So that can be used for W. You can see C plus D is feeding here. Similarly with X, we can take B dash common. It will be CD, and then we can also break C dash D dash into C or D inverter. So both these gates are being used here and here. Then in case of a Y, again, you take common CD, and we can break this one, not common, sorry. We can break this one down, so C plus D inverted. So that is used for Y. From here, you can see inverted. And then Z is D dash. So this is how a little modification can give us a slightly simplified circuit. The 3-level logic circuit requires fewer gates, all of which in turn requires no more than 2 inputs. I hope you have been able to follow this. Please let me know through your comments. Thank you.